Hello, this is Real World Audio, and it's time to continue exploring phono stage schematics. So we are looking at an example for an active phono stage and for a passive phono stage schematic, and I'm focusing on the uh, amplification stage, on the gain stage, and the RIAA correction. And for now, I am not looking at the power supply. So just the signal path for simplicity's sake, because I just want to point out what each of the elements are doing. So if you have any of these phono stages, you can learn from it. I'm showing what is good and what is bad with each of them, or I'm not even saying what is good and bad, but how things work and how you can change things for better or worse if you want to play or toy around with them. And I have a great familiarity with the Hagerman cornet because I have built the original version myself. Now Jim is already at the several. I think his is now the current one is the 4th generation, and I have not played around with the ear. So I'm just at the mercy of a schematics that I found online for it, and for voltages, because the voltages are not written here, so I just read it somewhere here on this forum. But apparently those plate voltages I read were not correctly given, because Dan shared a fantastic comment that he has an ear clone, ear 834p clone, and his plate voltages are quite higher than the ones that I read on that forum. So the first stage is 100 volts on the plate, second is 122 volts, and the cathode follower has 293 volts with B plus at 295 volts. So let's just go back here and let's read what we want to read. So basically these values actually make way more sense to me than the 65 volt at the plate here and 100. So basically what Dan was saying, that let's go back, he measured 100 and 122. So basically here, if you measure that point at the plate, then that's 100 volts, and here the plate of the second stage, that's 122 volts. And the supply that these tubes are getting here, that's 295 volts. So basically 300 volts, and it drops a little, and we have something close to 300 minus 122 volts. That's something. And we have to also subtract the voltage drop through this 20 kilo ohm resistor, which I don't know how much it is, how much voltage is dropped through that, because I don't know what are the currents running through these tubes. However, we can approximate that this load is around 160, 170 volts dropping through that that resistor there. So that means that actually does make sense, because if it's like around 170, and the current should be then half a milliamp, and that would give us that 330k resistor. So if you know how much voltage is dropped through a resistor, you can calculate what is the amperage, what is the milliamps that's being run through that. So I just did a quick head calculation that with that setting, this tube is drawing approximately half a milliamp of current. And this 2.2 kilo ohm cathode resistor is also telling us that it's drawing approximately that much current. And so basically this stage here is biased to run at half the current that a 12AX7 I would say in most operating conditions is running at. And the situation is similar here. The first stage is also run at a lower current than 12AX7s as usual. And how can you tell that? If you know a tube well, if you've been working with it a lot, then you can tell by looking that you have like a higher cathode resistor and a higher plate resistor than in most cases. So let's have another look here with the cornet. And with the cornet we have half the plate load and half the cathode resistor. So basically we have 0.9 kilo ohm, that is 910 ohm resistor, versus 2.2 kilo ohms at the ear. And here we have 330 kilo ohm and we have 150 kilo ohm. So roughly half what we get here. And also this goes with the higher voltages. So on the plate we get roughly 160 volts for both this first stage, both the second stage. And as you see, the operating conditions are set the exact same way for the first tube stages. And when we look at the ear, then these first two stages are run well, actually they seem to be running in the same condition because they both have 2.2 kilo ohm cathode biases, and both of them have 330 kilo ohm loads. So you would think that they are operating at the same operating points. However, check this out. Here, these two stages are separated with a 200 kilo ohm resistor. So basically, the plate resistor supply voltage will be quite a bit lower than the supply voltage for the second stage. So it means that these two tubes are essentially operating under quite different conditions. However, when you look at the cornet schematics, there is no power supply. Let me see. There is no power supply decoupling between these two stages. So we have that 47 microfarad capacitor here, bypassed by 1 microfarad capacitor. But that thing is common. So both of these tubes are fed from this common point. So the high voltage that these two tubes getting, that their plate loads are getting, are coupled. So there's no separation between the two. And now let's see, this is an advantage but also a disadvantage. So let's have a look first at the ear, because here what you see is that between this plate load resistor and that plate load resistor, there is this major 200 kilo ohm resistor that's almost as big as the plate load itself. So it means that it's dropping quite a bit of voltage. So this resistor here causing that lower supply voltage is the reason why we measure lower voltage on the first sections plate compared to the second stages plate. And the good thing with this is that when you have a resistor here and then that 47 microfarad capacitor, this is actually an additional pi filter that is added that will cut the hum down, and it will provide an even quieter supply for the first tube. And that's usually a very, very good idea, because the earlier your stage is in the signal path, the the quieter the supply, the better it is, because here the signal is very low level, so any hum coming from the power supply will be amplified many fold. So basically, now here we are dealing with 100 times lower signal level than at the second stage. So basically you want that much lower, you want 20 dB lower hum levels compared to what are hitting your second tube. So here we got a check mark for that, is that our first stage is getting a very quiet, well filtered B plus, high voltage in other names, and that's a good thing. However, here we do not have that advantage, so it means that the first stage is not getting an extra quiet B plus. So in theory, the ear has the ability to be a quieter phono stage. So it has the potential to have a quieter background noise level than the cornet. However, not having that decoupling between those two means that there is no delay, no phase delay between the two stages. So it means basically that they are getting the same power with the same phase angle, and that has a better sound quality in return. So basically that's a more preferred option, to have that kind of solution, that you are not decoupling them, and then the time constant, that's the name of it, the time constant is the same for both of these tubes. And actually that's also this type of topology is the secret of the Darling amplifiers. And when you build a Darling amplifier, if you try to upgrade it by, let's say that this is the power stage or power tube in the Darling amplifier, and this is the input tube, and if you try to put a resistor here and an extra capacitor to ground, then the sound quality will drop quite a bit, and you won't benefit from it, because the Darling amp is perhaps one of the top 10 most quiet amplifiers in the world. And here we actually have a similar scenario with the cornet. I don't think it would benefit if we would put a pi filter between these two stages, because it's ridiculously quiet, and I have 102 dB efficient loudspeakers, and I'm not having any detectable noise floor from the cornet, so it's not something that it ever bothered me, or I ever noticed that that sort of issue is there at the first place. So one thing in audio is that if it's not broken, don't try to fix it. So every additional step, every additional element that you add to make your circuit more complicated, it really has to serve a function. I would say when you experiment, try it out, and if it is an improvement, keep it. But if you find that it's detrimental, then just take it out again and don't leave it in if it does nothing, because along the road, sooner or later, you are going to see the downsides of it. And two of the positive things, one is that the time constant is the same for both of the tubes, and also these tubes are working in opposite phase. So it means that when this tube is increasing the current draw, that tube is decreasing the current draw. So they are kind of like working in a push-pull orientation regards to the power supply. So it means that when this tube's current is increasing, this tube's current draw is decreasing. So basically, without that extra pi filter, these two sections here represent a quasi-stable current draw for the power supply. If we would put a pi filter there, then this stable situation would be gone. And the other thing that I find that's very nice here is because there's no extra pi filter, no voltage drop, these two tubes operate in the same condition. So basically they cancel out each other's distortions. And this is used in Sakuma designs. He uses stages that follow each other, like for example a type 842 845 tube driving an 845, or whatever, like a 45 driving a 45, because when you have opposite phases, and here if you have like this plate out, you take the output from the plate, so it means that the second stage is mu follower, then they will be working out of phase. When you have the output on the cathode, then it will be the same phase as the input. So here they are working opposite phases, so basically they are doing a constellation of each other's distortion characteristics. It's not going to be as perfect as in a, let's say in a power amplifier, because here we have the RIAA corrections between the two, and that will skew the frequency domain content between those two tubes, but we still have a partial cancellation of the characteristic of those tubes. And I can tell you guys that out of every 12AX7 design I heard, the Hagerman phono stages, because the violin also has 12AX7 in the first two positions, they show the character of the 12AX7 the least. So it's not just theory, but it's practice as well, and Jim has done a really strapping job by employing this little trick to make the flavor of the tube not noticeable, not come through in his designs as much as it does through other designs. And there are some people who like that kind of sound that 12AX7 gives to the to a unit, but I would say that on the long run you don't want to have any kind of strong flavor modifying your music, and the 12AX7 flavor is kind of like thinning out, a little thinner, and that thinness gives a perception of added dynamics, but you lose a natural relaxation and body to the sound. And here Jim is making sure that we have that by the use of these two tubes without the pi section, the pi filter between them, and by running them using the same operating point. And also he's running them at higher current, around 1 milliamp or so per plate, and 160 volts on the plate. And now I have to say that this is absolutely crucial. What is the condition that you bias your tube to work at? Because if you bias your 12AX7 a different way, it will sound like a different tube, and it is almost, I would say, like a decades-long persuasion to find an optimal operating point for a vacuum tube. And for any and every amplifier, it is much, much, much more different to find the sweet spot for the tube, to bias it properly. This is, I would say, at least 10 times more important than the selection of vacuum tube itself. So when people are saying that I'm using this tube, I'm using that tube, I'm using whatever tube, like a magic tube, something that everyone really wants to have, that has secondary importance compared to how do you bias them. Because you can have the best driver tube in the world, if it's poorly biased, it's not going to live up to its potential. And if you have a tube like the 12EX7 family of tubes, which is actually more modest when we look at the ultra high performers, but when biased properly, it can deliver a very surprising performance. And here you read 12EX7, and of course for the AR ear also 12EX7, but it is understood that you can use any of the 12EX7 family of tubes like the ECC 83, E83CC, and a plethora of the military edition variants, which are the 4-letter code tubes. And basically that when it reads 12EX7, it covers at least, I would say, 50 different types of tubes that you can put in this position, which have the same pinout and which will run the same currents, which will have the same gain when biased up the same way. So whenever you read 12AX7 anywhere, then you know that you can basically put there any kind of tube. Of course, there is the manufacturer's recommendations. So for example, if they bias up the 12AX7 to run, let's say, like 1.5 milliamps of current, that would kill most of the 12AX7s very fast. But there are some rugged versions which were made for very high duty, for higher plate dissipation, like a long plate versions, and you can employ those in that position, and you have to, otherwise they will burn up. But if there are no such specific limitations, then here the word is your oyster in both the ears case and the cornets case. You can put here any kind of these family variants here. So now let's have a look at the RIAA, the correction. I think this is where I left off. So at the Hagerman, we have a 10 kilo ohm resistor in the signal path, and also a 220 ohm grid resistor, but that value is negligible compared to the 10K. So the total value is like 10.22K. That's between the plate and the grid of the second stage. So basically these two resistors and that capacitor there are in your signal path. And that capacitor there, 100 nanofarad, 20 years ago caused a huge problem, because that time the high quality coupling capacitors were much harder to get and very expensive. Today we have even more expensive capacitors to get, much more expensive than at that time. But at the affordable range, we have already extremely good capacitors that you can use, so they are no longer a big no-no if you want to build a very high quality phono stage. And there are these two additional filters here. So this actually forms the grid leak resistor of the second stage. This is not part of the RIA correction. However, this whole thing is there. Basically the 10K resistor, 6.8K, 47 nanofarad, 100 nanofarad. This is the RIAA correction. And this some of the phono stage makers, or many of them, just use some published values, and in the case of the 12AX7s, they go with very high resistances between the first two stages. And that's what the ear is doing as well. So here, actually, the RIAA correction is a little bit different, because what we are having here is that between the first and the second section there is just an amplification, and there's just a coupling capacitance and a 2 mega ohm grid leak resistor. And I would say here that 2 mega ohm is a really high value, and I don't like to use such high value resistors, because to get high resistance, it means you have to use a poor quality metal inside that resistor to manufacture them. The lower the resistance, the better quality the conductor is in that resistor. And once we go above 100 kilo ohms, then the quality, the sound quality, that I mean the impact on sound quality, the negatives, becomes exponentially higher compared to that of lower value resistors. And that's something that also is affecting the difference between 330K and Cornet's 150K. There's a jump there between the quality of resistors, how much they impact the sound. So for the Cornet you have a bonus there. But I would say that for the ear you can also try to lower the plate road resistor as an experiment. Try to go for 200K instead of this value, and you can also, if you want to try, lower these values here, because for the Cornet we also have the same. Does it say here? Look at that, where it is, 330 volts supplied to the cathode follower and 300 volts supplied to the plate of the 12AX7. And here basically we have technically 300 volts supplied here to these guys as a supply voltage. So basically, if you want, you can try out the Cornet's operating points to bias up your tubes. So 900 ohm, 910 ohm resistors for the cathode and 150K resistors for the plate, and you can try out what's the difference. But then you need to know that your current will increase, the current draw, so you can change this to a 10K resistor, and this one change it to 100K, because it's going to draw double the current. And with that you also need to double the wattage of each of these resistors that I'm pointing at, that you are changing. And yep, so that's one thing that you could do. But here you I warn all of you guys that it might not work, or it might work, I don't know, because here we have an active feedback situation. So there is a feedback loop, and it might get impacted by changing the operating points of the vacuum tubes. And here the feedback loops feeds back to the second stage, so you might get away just by little bit toying around with the first stage, because that's not part of the feedback loop. I hope that was understandable. But what I wanted to tell you guys is that here there's no RIA correction in the first stage. We just have a regular RC decoupling, and then in the between the second and the third stages, this is where the RIA correction happens. And the components that are part of the correction are the resistor here, capacitor there, and also a feedback loop around coming from after the cathode follower and going back to the input grid of this tube. So basically, the RIA has been split to two sections. And let me just stop this video because I won't be able to save it. It's getting too long.